Open ChatGPT, type a message, get a response in 2 seconds. Now keep the conversation going for 30 or 50 messages. Notice how each response takes a little longer. That's not your internet. That's the KV cache filling up. From earlier episodes, you know transformers use attention. Every token looks at every previous token, and inference generates one token at a time. So when generating token number 100, the model needs to attend to all 99 previous tokens. That means recomputing the same attention vectors over and over. Enter the KV cache. For each token, the attention mechanism computes 3 vectors. A query, what am I looking for? A key, what do I contain? And a value, what information do I provide? The trick is, only the query changes for each new token. The keys and values for previous tokens stay the same. So instead of recomputing K and V for every previous token every single time, we cache them. Process the prompt once, store all the keys and values, and for each new token, just compute its query and one new KV pair. That's the KV cache, and without it, inference would be orders of magnitude slower. But here's the catch. How much memory does this actually use? The formula is 2 times the number of layers times KV heads times head dimension times sequence length times bytes per value. For Llama 3.170B at full 128K context, that's 42 gigabytes of VRAM for one user's conversation. This is exactly why conversations slow down. 2 things compound. First, growing attention cost. Each new token must attend to all cached tokens. At 1K context, it's fast. At 100K context, it's attending to 100,000 key vectors. Second, memory bandwidth saturation. The entire KV cache must be read from VRAM for every single generated token. So when the context window fills up, something has to go. The simplest strategy is FIFO, drop the oldest tokens. But here's the problem. The system prompt is the oldest and often the most important. FIFO drops it first. Not great. Most production systems use a smarter approach. Keep the first N tokens for the system prompt, keep the most recent M tokens, and drop everything in the middle. There's also attention-based eviction, drop tokens that the model barely looks at. More sophisticated but computationally expensive and still a research area. Mistral popularized a completely different approach, sliding window attention. Instead of caching everything, use a fixed window of recent tokens. Token 100 only attends to the last 4,096 tokens, not all previous tokens. Memory stays constant no matter how long the conversation gets. But won't it forget everything outside the window? Not entirely. Through multiple transformer layers, information propagates. Layer 1 sees 4,096 tokens back. Layer 2 indirectly sees 8,192. With 32 layers, the effective context reaches about 131,000 tokens, even though each layer only looks at 4,096. The biggest innovation for reducing KV cache size. Share key and value heads across multiple query heads. Standard multi-head attention gives every head its own Q, K, and V. That's 64 of each. Multi-query attention shares just one KV pair across all 64 query heads. That's 64 times smaller. Llama 3.1 uses the middle ground grouped query attention with 8 KV heads for 64 query heads. That's 8 times smaller than standard attention. And just like model weights, you can quantize the KV cache too. Going from FP16 to INT4 takes that 42 gigabyte cache down to just 10.5 gigs. So to recap, the KV cache is what makes AI inference practical by avoiding redundant computation. But it grows linearly with context, eating massive amounts of memory. Production systems fight this with grouped query attention, sliding windows, cache eviction, and quantization. Next episode, what happens when 1,000 users hit your model at once? That's the batching problem.